Hi everyone, my name is Jing Wei and I'm from the University of Melbourne, Australia. In this video, I'll present our work called What Could Possibly Go Wrong When Interacting with Proactive Smart Speakers, a case study using an ESM application. To start, please take a look at my Proactive Smart Speaker prototype. This prototype is built based on the commercial Google Home. Through the very cute tiara, I attached a pair of earphones onto the speaker. The earphones are powered by a Raspberry Pi, where I store a few pre-recorded audio commands. Whenever I want the Google Home to be proactive, I can simply control the Raspberry Pi to play audio commands. The speaker will then be triggered. In the meantime, I built a very simple ESM application to run on the speaker. Here's an example dialogue.
Rate your availability on a scale of 1 to 5. 1. Rate your boredom level on a scale of 1 to 5. 1. Rate your current mood on a scale of 1 to 5.
5.
What are you currently doing?
Attending Chi.
Thank you for your time.
As you can see and hear, the dialogue is very simple. The speaker asks 3 numerical scale questions and 1 open-ended question, and the user simply answers 3 numbers and 1 free-form response. Before deploying the speaker prototype and the ESM application, I was quite confident about the system. I mean, how hard could it be? All the speaker needs to do is to accept 3 numbers from 1 to 5 and whatever input for the last question. Some errors may still be possible, but there shouldn't be a lot of errors. So I recruited 13 participants and deployed the prototype in their homes for 3 weeks. I scheduled the speaker to proactively prompt the ESM every hour from 9 a.m. to 9 p.m. We successfully collected 1,213 ESM responses. The response rate is about 35%, which seems quite decent, right? But among those ESMs, we find that only 85% are fully answered, while the rest 15% contains missing data. Before I show you more details about the incomplete ESMs, here is a breakdown of those complete ESMs. Surprisingly, many ESM interactions contain error. As you can see here, only about 63% ESMs were answered without triggering any interaction errors. Around 24% ESMs had 1 error and the rest ESMs had more than 2 errors. Usually, it is no big deal to have 1 or 2 errors and most people are tolerant with that, but we later find that the time cost of errors is very high. Now let's take the bottom question as an example. On average, it took 10 seconds to answer the question. However, you can see that 1 error can cost more than 12 extra seconds. And with 2 errors, users need to spend almost 30 seconds more to answer the question. The time cost is really high. You may wonder, what if 3 errors occur? Currently, for Google Home, the interaction will be terminated after 3 errors have occurred. So when I was first looking at all the missing data, I thought, those ESMs must be terminated because of continuous errors. But after I listened to some audio recordings from study, I discovered another type of termination errors. I call it sudden termination. Here's an example.
Rate your availability on a scale of 1 to 5.
5.
See you later, alligator.
As clearly demonstrated by the conversation, Google misrecognized 5 as buy, and instead of triggering the error message, it treated buy as a higher priority command and terminated the ESM suddenly. In fact, STs occur 6 times more common than ATs, and 5 or buy is not an individual case. There are other cases. For example, when a pool was recognized, the speaker would just terminate the ESM and start announcing nearby swimming pools. With a lot more manual efforts, we even found that there were 30 more times where participants attempted to answer the first ESM question, but those ESMs were terminated before any responses were recorded. To overcome errors, our participants adopted several strategies. The first one is raising voice and approaching. Overall, this is a good strategy. Another strategy is repetition. You may think this is also a good one, but repetition can cause two issues. The first is that if the user repeats the answer due to silence from the speaker will constantly receive new information and send that to the cloud. In the end, the speaker will have more delays waiting for the information from the cloud. Also, repetition can cause double response errors. The third strategy, phonetic and lexical changes, has been reported by many other researchers. Changing answers phonetically, such as changing the pronunciation, usually does no harm, but lexical changes really hamper data quality. We find that our participants also sense that some numbers were hard to be recognized. So when facing recognition errors, they will simply change their answers. About 9% ESMs in our dataset contain those changed answers. One extreme case that we found was one participant literally uttered all 5 numbers to one question during one interaction session. Lastly, another unexpected strategy was help from others. Collaboration is usually found to be a way to resolve interaction errors. In our case, however, such collaboration usually means that the non-targeted user reported answer on the targeted user behalf. This is a very bad strategy for data collection purpose. To sum up, we think our participants strive to give recognizable answers rather than giving genuine answers. Although I have just shown you what actually went wrong during my study, I want to emphasize that I believe smart speakers can be a very useful platform for collecting user data. Therefore, I want to provide some design implications. The first is to use better words. Some studies have shown that short single-syllable words can be difficult to be recognized. Unfortunately, numbers from 1 to 5 are mostly those bad words. Therefore, researchers can consider using other words to replace numbers. The second suggestion is to use fewer open-ended questions. In our dataset, 26.4% free-form answers need post-hoc manual transcription. Researchers should really think about the amount of manual effort in conversational data collection. Lastly, we need to think about reducing the delay. Currently, everything is processed over the cloud. Network routing and latency can cause confusion and bad strategies, so I would suggest developers to choose cloud servers closer to targeted users. For example, as I'm in Australia, I will not choose the US Central Server in the future anymore. Lastly, I want to provide the research implications. Most of our findings are only found by manually listening to audio recordings captured during the study. The speech recognition technology is not yet perfect and won't be perfect in the near future. Therefore, future researchers need to learn what users actually said and what speakers actually heard. One way is to use audio recording and keep a track of conversation logs. Of course, we should protect participants' privacy and collect data ethically. That's it. I hope you enjoyed my presentation. Feel free to reach out to me via email. Just like my speaker prototype, I'm open to all sorts of conversations. Thank you. Bye.